Hey there, grade 11s. Today we're going to correct the mass-mass stoichiometry, or we're going to at least do a warm-up with mass-mass, and then we're going to go through how to solve any stoichiometry problems. So we're just going to be bringing in some of the other mole highway conversions that we've done in the past. So what I would suggest is try warm-up number 13, give it a shot on your own. So I'd pause the video now and then come back and you can play the video and walk through the solution. So here's the solution. So if we're looking at this reaction, we'll actually do this reaction in the lab. This is hopefully when we get back we can do this lab. You're taking baking soda and reacting with hydrochloric acid. You're making water, carbon dioxide, and salt. So now we have a measured amount of baking soda. If we put it in enough acid, whatever amount of acid we want, and as long as there's extra, the baking soda is going to get used up and it will make a certain amount of the salt. And that's what we're going to calculate. We can actually calculate fairly accurately or very accurately how much salt we should get. So the first step is we always have a balanced reaction, which they've given us in the question. The next step is to convert whatever we have to moles. So we have this 0.75 grams here, so I'm just going to take that and change it to moles. So baking soda, sodium hydrogen carbonate, weighs 84.01 grams per mole, so that's how many moles of baking soda we have. Then the next step is we want to use the moles of the baking soda that we have, which is here, and we want to find the moles of salt that we're going to make. And the ratio is nice and easy. It's a 1-to-1 ratio from the reaction. So I'm just going to convert from moles of baking soda right here to moles of salt by putting baking soda on the bottom and salt on the top. So now we're going to make the same number of moles because, again, 1-to-1 ratio. But now here's where we can find the grams of salt. If we have the moles, we're going to take the molar mass of salt and convert it to grams. And here we go. We get 0.52 grams of salt. Now again, something I like to stress with my students when we talk about stoichiometry is I want you to really notice that the mass of baking soda and the mass of salt are different, even though the ratio is 1-to-1. And the reason for that is baking soda and salt have different masses. So 1 gram of baking soda does not make 1 gram of salt, but 1 mole of baking soda will make 1 mole of salt. They're related through the number of things, not their masses. Anyways, okay, so today we're going to just kind of combine things together, and that means we're going to finish off our notes on stoichiometry. So we're down here, solving any stoichiometry problem. So it should look something like this. So again, we don't have to deal with just masses. We can be given any units we have and go put our answer in any units they ask for. So here are all the different units we have to work with that we've been working with so far. Eventually we'll get molarity in there, but that's coming down the road. So the first thing we have to do always is write our balanced reaction. And then once we've got that, whatever units, whatever amounts you're given in the question, change it to moles. Because like I just said, our amounts are related through moles, not through grams. Once you've got that, now we'll set up our mole ratio between what we have and what we're trying to find. And we'll cancel out what we have and try to figure out how many moles of what we want or what we're looking for. And then whatever we have at that point, we just convert to whatever unit the question wants us. Moles, grams, liters, whatever. Now there's a couple things we got to make sure. All of our masses must be in grams, and the reason for that is because molar mass is in grams per mole. So when we have a mass, we have to change it to grams if it was in kilograms. And our volumes, if we're talking about gases, the volume has to be in liters. We can't work in milliliters. So remember that 1 liter is 1,000 mils and 1 kilogram is 1,000 grams. Okay, so the easiest way to do this is just to go through some questions. It's really the same thing we did yesterday. We're just using different unit conversions. So it's just changes in the mole highway part. Here we go. So it says find the volume of ammonia produced when 3 liters of nitrogen gas reacts with hydrogen gas. Now there's a shortcut to this one, but I'd like to follow the same process every time because for right now, we just want to get that process down. So the first things first is we'll write our balanced reaction. So we have nitrogen gas and hydrogen gas making ammonia. And the ratio or the balancing would have to look something like this. I need 2 nitrogens there, which means I need 3 hydrogens there. All right, we're going to start with our 3.0 liters of N2, and we want to change that to moles right away. So I'm going to get rid of liters and put moles in its place. We know that 1 mole of any gas is 22.4 liters, so we get 0.13 moles of N2. Now we have this chemical. We're trying to find this one. So the ratio is 2 moles of NH3 for every 1 mole of N2. So that will end up being 0.26 moles of ammonia. Now the question wanted me to change that to volume, so I'm going to times by liters and divide by moles. And again, we know that 22.4 liters will have a mole of gas in it. So we end up with 6.0 liters of NH3. Now some of you might say, well, look at the 3 and the 6, it's just doubling, and that kind of makes sense because this is doubling. That's kind of the shortcut I was talking about. If your units are staying in liters, we can just go from liters to liters because the molar volumes are the same for every gas. But if I change the units in there, then that would fall apart. So I'd rather we just follow this process. That way then we get it right. So here's another example, same idea, but now I've got one of the units in grams instead of both units in liters. So first thing we got to do is write our balanced reaction. We're burning some methane. Methane is CH4. They gave us that in the question. So it's CH4. If it's burning, it's reacting with oxygen, and our combustion reactions will always make carbon dioxide and water. So now we go back and balance. The way we do our balancing is carbons, then hydrogens, then oxygens. So carbons first, they're balanced. I need 2 there for the hydrogens. So that gives me 4 and 4. Now I need 2 more oxygens there, and now we're balanced. So now I'm going to take my 55 grams of methane. I'm going to get rid of grams, so grams on the bottom, moles on the top. 1 mole of methane weighs 16.04 grams. So that gives me an answer of 3.43 moles of methane. Now we have this, we're trying to find this. So the ratio, 1 to 1. So 1 mole of CO2 is made every time we use 1 mole of methane. So 3.43 moles of CO2 are going to be made. Now we're trying to find the liters of carbon dioxide. So I'm going to get rid of moles and put liters in its place. And again, we know that 1 mole of any gas takes up 22.4 liters of space. So this would be 76.8 liters of carbon dioxide. So that would be the volume from burning only a little 55 grams worth of methane. You get 76 liters of carbon dioxide gas. So next question is, how many grams of carbon dioxide are produced when 55 liters of methane? So we're just doing the same question, but with the reverse units. So same deal. Methane, again, is CH4 plus O2 makes H2O and CO2. I guess I flipped that around this time, but it doesn't really matter. So I needed a 2 here, which means I need a 2 here. So we have our 55 liters. So 55 liters of CH4, and we're changing this to moles. So 1 mole over 22.4 liters, and that will give us 2.46 moles of CH4. And now we need to go to carbon dioxide again, so it's still the 1-to-1 ratio, 1 mole of CO2 for every 1 mole of CH4, so 2.46 moles of CO2. And now we're going to convert this to grams, so 44 grams per 1 mole gives me 108.04 grams of CO2. And there's your answer. Okay, so for the next 2 questions, they're the try these ones. So what I'm going to do is I'll take a second here and I'll write the answers. I'll put the solutions up, but you may want to stop the video and try them on your own and then resume so you can see if you did it right. Now this example we already did, so I'm skipping it. There we go. Try this one, number 1. So we have nitrogen gas and hydrogen gas making ammonia. And it actually looks like we just did this exact question in the notes, except for the difference is we're being asked to find grams this time. NH3. So we need 2, 3. So we have 3 liters of nitrogen gas. 1 mole, 22.4 liters, 0.13 moles of N2. And we're going to ammonia. So we're from here to here. So 2 moles of NH3 are made every time we use 1 mole of N2. So this will be 0.26 moles of NH3. And now we're trying to find the grams. So I put grams on top, moles on the bottom. 1 mole is 17.03 grams. And I get an answer of 4.56 grams of NH3. Now for the next one, if your question happens to be slightly different, please change it to match this one because I fixed something in the notes here, but the balance reaction should look something like this when it's actually balanced. So you put a 2 there and a 2 there. So now we're going to start off with our 4.5 liters, and we're going to figure out how much of the glucose we actually have to use up to make that. So 4.5 liters of CO2. We're going to change this to moles. So 1 mole, 22.4 liters, 0.2008 moles or 0.2 moles of CO2. And now we're going to find, we have this, we want to find this. So 1 mole of C6H12O6 for every 2 moles of CO2. So this will be 0.1 moles of C6H12O6. And now we're going to multiply by the molar mass to get the grams. So grams per 1 mole. And it's 180.12 grams. So I got 18.01 grams of sugar. There you go. So next on your agenda would be to work through the stoichiometry mix questions. Give those a try, and we'll touch base on Monday.